Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light. In my previous two lectures, we began to discuss the work of Hermann von Helmholtz, his lecture titled On the Conservation of Force. There we introduced the concept of quantity of work. You might recall we had a discussion of a pendulum clock where a weight drives the clockwork. How much work is done can be computed from the weight multiplied by the distance through which the weight falls. That weight, in falling through a distance, does a quantity of work that can be computed in terms of foot-pounds, or if you prefer the MKS system of units, Newton meters. In this lecture, I want to talk about a few applications of this concept. Specifically, if we look at page 106, Hermann von Helmholtz shows what is called an overshot wheel. An overshot wheel is a device which uses the force of gravity, which causes water to fall, of course, in order to accomplish work. This is an ingenious device. We can think about it in this way. Just as the falling weight in a pendulum clock is able to turn gears, so too the falling weight in an overshot wheel is able to turn gears or grind wheat or lift weights or whatnot. So if we imagine schematically what's going on here, we can draw a wheel like this, and we have some kind of plank or a board that the water runs over. So we can imagine having water running over the board in this way and shooting over the top and landing in a bucket. So the bucket might be located right here. It's attached to the wheel, and when the bucket fills with water, it falls down. And so there's a force of gravity that acts on the water in the bucket that points downward, and as a result, that bucket descends by some distance d. And so what happens, we can compute the work accomplished is going to be equal to the force of gravity times the distance or the height through which that water falls. Now you might imagine that what we could do is, if we were clever about this, we could put a shaft on this wheel, and as this shaft turns in this direction, we could have a rope wrapped around this shaft, and the rope could be attached to a weight that we would like to lift. And so as this water falls on this side, this weight over here would be lifted. So this can lift a weight. That is schematically what's happening. Of course, we could just grind wheat, or we could use this to turn magnets in order to generate electricity. That's a modern application of this. Let's suppose that we were to have a ceiling right here. And from that ceiling, we were to hang a rope. We're to fix a rope right here. And that rope were to be threaded underneath a pulley. So the pulley is right here. And to that pulley is attached a rod with a weight on the end of it that one wishes to lift. And then we were to take another, if we were to pass this rope over the top of another pulley, we could then pull on the other end of the rope so as to lift the suspended weight. So this would be a fixed pulley, and this would be a movable pulley right here. And the idea is that pulleys allow a small force to lift a large weight. How do we analyze a situation like this using the concepts that Helmholtz has introduced? Well, if we were to apply a force, a downward force over here, we'll call this force input. And in so doing, we were to pull this down by some distance d input. That's the distance one would have to move their hand in order to pull down on this weight. You might see that in doing that, this weight right here is lifted up. So in doing that, there's an output force. Force output. And what happens is this mass goes up by a distance d out. Now here's the interesting thing to notice. One can compute the input work. The work one does in moving one's hand downward by applying the input force. That would be the force input times the distance input. That might be, for example, we could make up some numbers here. You were to apply a 50-pound weight and you were to move your hand downward by 1 foot. And so the input work one would accomplish would be 50 foot-pounds. Okay? Now, if we do this, the law of conservation of force, or we might say the law of conservation of energy, says that whatever work we put into this system must be equal to the output work. The output work must be equal to this. It must be 50 foot-pounds. But the output work is how much work we're doing on this mass over here, the risible mass. Now you might see right away that as you pull this string down by some distance of 1 foot, that mass is not going to rise by the same amount. Let's suppose we pull the string down by 1 foot. What's going to happen is that the mass is not going to rise by 1 foot. Instead, it's only going to rise by half of a foot. That's because the slack is being pulled up in the rope, and there are basically 6 inches of rope pulled up from each side of the pulley. So the output work would be the force output times the distance output, and the distance output is only going to be a half of a foot. That is, we raise this mass by only a half of a foot. But in order for the output work to be equal to the input work, that is 50 foot-pounds, we have to be able to lift twice as big of a force. In other words, we could lift a 100-pound weight by half of a foot. So a 50-pound lifting force, F input, can raise a 100-pound F output, provided, as we've done with the pulleys, that the amount that it's lifted is half as far. So, but the distance moved d out is going to be equal to 1/2 of d in. That's the principle of how pulleys provide a mechanical advantage. Some of you may be aware of this if you've ever worked out in a weight room. They have pulleys set up, and sometimes you can lift very heavy weights with a much smaller force, but you have to move your arm through a much larger distance. That's the exact same issue that we're talking about right here.